Hello students, welcome to the class. In the previous class, we have discussed regarding the different gas laws. Yes, and here is the description of the different gas laws, what we have discussed. Boyle's law we have discussed. What does Boyle's law stand for? Says it says that at constant temperature, the pressure is inversely proportional to volume. Yes, it is inversely proportional to volume at constant temperature. That is, when you increase the pressure, the volume decreases. When you decrease the pressure, the volume increases at constant temperature. Yeah, and when you plot a graph, what graph you get is called what? It is called isotherm. It is called isotherm. Then Charles' law we have seen. It says that at constant pressure, volume is directly proportional to absolute temperature. That is, as pressure increases, as temperature increases, the volume also increases. The volume of fixed amount of gas also increases, and it is directly proportional to absolute temperature at constant pressure. So the graph plotted is called what? It is called isobar. It is called as isobar. Next, what we have discussed is Gay-Lussac's law. It says that at constant volume, the pressure of the gas is directly proportional to temperature. That is, when you increase the temperature, the pressure also increases. Pressure of fixed amount of gas also increases. And the graph plotted at constant volume is called isochore. It is called isochore. This is what we have discussed. Apart from this, we have discussed one more law, that is Avogadro's law. Yes, what is Avogadro's law? Volume of fixed mass of gas is directly proportional to what? It is directly proportional to the number of moles. That is, where if you take equal volumes of any gases at Tp contain equal number of molecules, and that equal number is how much? It is nothing but Avogadro's number, which is equal to 6.022 into 10 raised to 23 entities. It might be molecules, it might be atoms, it might be ions. Okay, then ideal gas equation. What do we mean by ideal gas? Ideal gas never exists. See, okay, a gas that follows Boyle's law, Charles' law, Avogadro's law strictly is called ideal gas. Yes, a gas which follows all the laws, gas laws very strictly, is called ideal gas. Real gases, the gases exist in the nature are not ideal gases. They are real gases. Because I don't say that they do not follow these laws. They do follow the laws under certain specific conditions. Under certain specific conditions, when the forces of interactions are practically negligible, and it is not possible. There will be some force of interaction, right? Whether we are talking about attractive forces or repulsive forces. Now, ideal gas equation. This equation is nothing but it is a combined equation of the three laws. Yes, what three laws we will use? We'll see it, and it is known as ideal gas equation. The ideal gas law is the equation of the state of hypothetical ideal gas, imaginary ideal gas. It is a good approximation to the behavior of many gases under many conditions, although it has several limitations. And this is the equation. PV is equal to nRT, where P stands for pressure of the gas, V stands for volume of the ideal gas, N stands for amount of ideal gas measured in terms of moles, R stands for universal gas constant, and T is the absolute temperature. T is the absolute temperature. So this is all about ideal gas equation. Fine. Okay, let us see how this ideal gas is derived. It is the combination of three laws. Okay, I'll just tell you how it is derived. We know that according to Boyle's law, what Boyle's law says? Boyle's law says that pressure is inversely proportional to volume, or I can say volume is inversely proportional to pressure, and this is at constant temperature. Okay. Second, according to Charles' law, what Charles' law says? It says pressure, volume is directly proportional to temperature at constant pressure. When you keep the pressure constant, volume is directly proportional to temperature. And one more law what I'm going to consider is according to Avogadro's law. What does Avogadro's law says? It says volume is directly proportional to number of moles at constant temperature and pressure. at constant temperature and pressure. Now see, volume is inversely proportional to pressure. It is directly proportional to temperature. It is directly proportional to number of moles. So when I combine all the three equations, equation 1, equation 2, and equation 3, what do I get? I get volume. It is directly proportional to number of moles. It is directly proportional to temperature, but it is inversely proportional to pressure. This is what I get, right? Remove the proportionality sign. I can write volume is equal to N. The proportionality sign constant is R, T upon P. Take this P on the left hand side. We will get PV is equal to nRT. PV is equal to nRT. This equation is called as, ideal gas equation. Ideal gas equation. It is called as ideal gas equation. PV is equal to nRT. So according to Boyle's law, volume is inversely proportional to pressure at constant temperature. According to Charles' law, volume is directly proportional to temperature at constant pressure. According to Avogadro's law, volume is directly proportional to the number of moles at constant temperature and pressure. So V is directly proportional to number of moles as well as temperature according to these two laws, and inversely proportional to pressure according to Boyle's law. Remove the proportionality sign, introduce a constant R, and this constant R is known as universal gas constant. Universal gas constant. It is called as universal gas constant. Take P this side. So PV is equal to nRT. This is called ideal gas equation. This is called ideal gas equation. Yes. So this is how we derive the ideal gas equation. PV is equal to nRT. Now, as I said, R is what? R is the universal gas constant. From this equation, can I see what is R? R is equal to what? It is PV upon NT, correct? PV upon NT. That is nothing but pressure into volume upon mole into temperature, correct? Therefore, what is pressure? It is nothing but force per unit length. Therefore, force per unit area. So, force upon area is pressure into volume divided by N is what? Number of moles into temperature, correct? Yes. Okay. So here I can write force by area into volume upon force into volume is what? Force into volume is work or energy. Force by area into volume. Force by area into volume is what? It is work, or you can call it as energy, or energy divided by mole into temperature, correct? Therefore, what will be the unit? What will be the unit of R? I just wrote it to find the unit. Force, so it is nothing but energy per mole. Energy per mole per Kelvin, correct? So energy per mole per Kelvin, because this is temperature, correct? So since there are different values for R, you can write different values for R. For example, the SI unit of R is, the SI unit for R is, value of R is 8.314 joules per mole. Energy unit is joules per Kelvin. This is the SI unit of R, that is universal gas constant. One more commonly used unit is R is equal to 0.0821 liters atmosphere per mole per Kelvin. Yes, or joules you can write it as Newton meter. So you can also write it as 8.314 Newton meter per mole per Kelvin. Yes, there are different ways of representing. Even you have 1.99, that is 2 calories per mole per Kelvin. Yes, there are many values for R, that is gas constant, universal gas constant R. Okay, even we can express this equation. PV is equal to nRT is what? This is ideal gas equation, correct? What is N? N is nothing but number of moles, correct? N is number of moles. And we know that number of moles is equal to given mass upon molar mass, correct? Substitute it. Therefore, I can write PV is equal to given mass upon molar mass, substituted the value of N into RT. into RT. Okay, we know this. Okay, I will take M on the other side and all the other terms on the other side. So I can write it as M is equal to MRT upon PV. MRT upon PV. And what is volume? What is density? We know that, I'll write it here. We know that D is equal to M by V, mass by volume, density. Here V is there, therefore what is V is equal to M by D. So it is in the denominator, therefore I can write M is equal to, see, M by V is already there. M by V is what? M by V is density. M by V is density. So D RT upon P, correct? So M by V I substituted. I can write it like this. M is equal to M by V into RT upon P, correct? RT upon P. So M by V is what? D RT upon P. Take D one side. So it will be what? D, I'll keep it here. It will be PM upon RT. PM upon RT. Yes. So what is D? Density. P is pressure. M is molecular mass. R is universal gas constant. And T is temperature. Or I can also write it as DT upon P is equal to what? It is equal to M by R. It is equal to M by R, and molecular mass, and this is universal gas constant. Molecular mass remains constant. Therefore, that is equal to what? It is equal to constant. It is equal to constant. Therefore, dt by P is equal to constant, or dt is equal to constant into P, or I can write it as directly proportional to T. So the product of density and temperature is directly proportional to what? It is directly proportional to pressure. Yes. So gas densities differ from those of solids and liquids. So gas densities are generally stated in how? Grams per liter instead of grams per cc. And from these all equations, we come to the conclusion that, see, look here, we come to the conclusion that I can write this like this also. D is proportional to P and inversely proportional to T. So it is density is directly proportional. We have seen this also. It is directly proportional to pressure and inversely proportional to temperature. Inversely proportional to temperature. Correct? Directly proportional to pressure and inversely proportional to temperature. Okay. So they are strongly dependent on pressure and temperature. I can say the density is strongly dependent on temperature and pressure. If you want to measure the density of a gas, density of gas at STP, you can say it as M upon Vm. What is Vm? M upon 22.4 liters. Molar volume, 22.4 liters. So this is the density of gas at STP. At STP. Yes. So this is all about ideal gas equation. This is all about ideal gas equation. Okay, let us see. See, at constant temperature and fixed amount of gas, volume is inversely proportional to pressure. It is Boyle's law. At constant pressure and fixed amount of gas, volume is directly proportional to temperature, Charles law. At constant pressure and temperature, volume is directly proportional to number of moles, Avogadro's law. All the three directly proportional to N and T, inversely proportional to P. R N T upon P, PV is equal to N RT. R is called gas constant. It is also called as universal gas constant. And what is value for R? PV upon NT. Substitute. This is 1 atmosphere. Okay. Pressure 1 atmosphere, 22,400 cc by 1 mole. You will get the value 82.1. See, different values are obtained for universal gas constant. And these are the values. So the first one, what you are seeing, this is the SI unit. This is the SI unit for R, universal gas constant, 8.314 joules per mole per Kelvin. This is 0.0821 you can take, liter atmosphere per mole per Kelvin. These two are most frequently used. Even M cube, cubic meter atmosphere, if you see, it is 8.205. Calories 1.99, that is 2 almost. Then mm of Hg, millimeter of Hg, mercury. So 62.363 millimeter of mercury liter per mole per Kelvin. Again, Ft. This is another value. This is another value of R. Different what you say, based on different units, the R value differs and it is a constant. We usually use these two values. 8.314 joules per mole per Kelvin, 0.0821 liter atmosphere per mole per Kelvin. Whereas these are the different values. Is that clear? Moving to the next one, Dalton's law of partial pressures. So what does this Dalton's law of partial pressure tells us? What it speaks about? Let us try to understand. Yes, what does this partial pressure means and what Dalton has spoken regarding his law of partial pressures. So what does the law says is, when two or more non-reactive gases are enclosed in a vessel, the total pressure exerted by the gaseous mixture is equal to the sum of partial pressures of the individual gases. Let P1, P2, P3 be the pressures of three non-reactive gases A, B, C, when enclosed separately in the same volume under same conditions. Okay. Okay, they have considered two gases here. They have named the gases as gas 1 and gas 2. Okay, so let us say we have taken two gases and the two gases should be non-reactive. They shouldn't react with each other. They should be non-reactive. Okay, understanding? So when you take the two gases separately, you know that gases exert pressure. Yes, the pressure exerted by individual pure gas, pressure exerted, you know gases exert pressure, right? So pressure exerted by pure individual gas is known as what? It is known as partial pressure. Partial pressure. Yes, so it is denoted here P1. So it is partial pressure with respect to gas 1. This is pressure exerted by the individual pure gas 2. So this is P2, partial pressure with respect to 2. Yes, so what Dalton's law says is, when you take a two or more non-reactive gases, the gases should be non-reactive. Means what? They shouldn't react with one another and form a new compound, new chemical compound, right? So when you take a mixture of two or more non-reactive gases, yes, when two or more gases which do not react chemically, they are placed in a closed vessel, the total, you mix them and take, combining the gases. Yes, so the pressure exerted by the mixture, what pressure is exerted? It is indicated as P total. The pressure exerted by the mixture is equal to what? It is equal to the sum of partial pressures of the individual gases. So this gas exerts, say, pressure P1. This gas individually exerts pressure P2. You mix both the gases which are non-reactive. The total pressure exerted by this mixture will be equal to the sum of the pressures exerted by the individual gases. Therefore, we can say P total, suppose you have n number of gases, you have mixed n number of gases, you will say it is the sum total of n number of partial pressures of n gases. So I can write as P1 plus P2 plus P3 plus P4 and so on up to Pn if I have taken n number of gases. Where P total is what? The total pressure exerted by the mixture of the gases. P1, P2, P3 are what? They are the partial pressures of the respective gases. 1, 2, 3, 4 up to n. Yes. So what do we mean by partial pressure? Very important concept. So what do we mean by partial pressure? Yes, partial pressure is what? It is the pressure exerted by a gas when it is present in pure state. When it is present alone, you can say. The pressure exerted by the gas when it is present in alone in the same container at same temperature. At same temperature. Yes, that is nothing but partial pressure. Yes, so if there are two gases, let me say there are three gases. And what is the condition to explain this? The three gases should be non-reacting. They should be non-reacting. They should not react with each other. They should not react with each other. Then when you combine, so they will exert some pressure. We know they will exert some pressure. Yes or no? So let me say this is my gas A. This is my gas B. This is the gas C. Yes, so these molecules are present in a closed vessel of gas A. These are the molecules present of gas B, and these are the molecules present of gas C. Yes, so individually they will exert some pressure across the walls of the container. That is called partial pressure, denoted as P1, PA. Okay, and this will also exert some pressure. It is PB, partial pressure with respect to gas B. This is partial pressure with respect to gas C. When you mix all the gases, combine all three gases, what will happen? You combine all three gases. Here you will have mixture of all the three gases. And the gases should be how? They should be non-reactive. Therefore, they will exert some pressure here. So that is what? That is total pressure. So what is total pressure here? The pressure exerted by the mixture. That will be equal to what? It will be equal to the sum of pressures exerted or partial pressures exerted by the individual gases. That means pressure of gas A, pressure exerted by gas B, pressure exerted plus pressure exerted by gas C. This is nothing but Dalton's law of partial pressures. Dalton's law of partial pressures. Is that clear? So Dalton's law of partial pressures, we explain it as, it is a gas law which states that total pressure exerted by a mixture is equal to the sum of partial pressures exerted by individual gas in a mixture. For example, if you take total pressure exerted by the mixture of three gases A, B, and C, it will be equal to what? It will be equal to sum of individual partial pressures exerted by gas A, by gas B, and by gas C. With this, we have a Dalton's formula. Yes, we have Dalton's formula for partial pressures. Yes, so understood. This is, so Dalton's law of partial pressures can be mathematically expressed as follows. P total, what is P total? The total pressure exerted by the mixture of gases, non-reacting gases. Summation of N to I equal to 1, or we will write it and Pi. Yes, or we will write it as P total is equal to P1 plus P2 plus P3 and so on up to Pn, where P total is what? It is the total pressure exerted by the mixture of gases, and P1, P2, P3, Pn are what? They are partial pressures of gases 1, 2, 3 and so on up to N in a mixture of N gases. Yes, in a mixture of N gases. So this is called Dalton's law of partial pressure. Now, expressing this partial pressure in terms of mole fraction. See, in the, what you say, in your first topic itself, we have discussed what is mole fraction, right? Can you just recall and tell me what is mole fraction? Mole fraction, it is to express the concentrations, we use different terminologies, and one is mole fraction in that. Do you remember mole fraction denoted by X? What do we mean by mole fraction? It is nothing but number of moles of a component divided by total number of moles. Total number of moles, correct? This is mole fraction, yes or no? So if suppose I say I have a mixture, let me say I have a mixture here. I have mixture of two components, A and B. So how do I write mole fraction of A? Mole fraction of A is equal to number of moles of A upon total number of moles. Number of moles of A plus number of moles of B, correct? So number of moles of A plus number of moles of B can be written as N, total number of moles. So I will write mole fraction of A is equal to what? Na upon N, where N is what? Total number of moles. Similarly, how do I write mole fraction of B? I will write it as Nb upon N. That is Na plus Nb, you can see. Nb upon N. Or we know that mole fractions of the components is equal to unity always. Therefore, if you know mole fraction of A, you can calculate mole fraction of B as 1 minus the mole fraction of A. And mole fraction is a unitless quantity. This is all we know regarding mole fraction. Now, what we are going to discuss is the relationship between partial pressure, expressing the relationship between partial pressure and mole fraction. And mole fraction. Yes, we see what is given here. Okay. Let at the temperature T, three gases enclosed in the volume V exert a partial pressure. So we know T is temperature, V is volume, certain volume V at certain temperature T. So exert pressures P1, P2, P3 respectively. Yes, so these are the three gases, let us say. According to Dalton's law of partial pressure, how do you write? We write it as, we'll come here. We'll consider like this. Okay. So let me say I have these three gases. Fine. Let me say this is gas 1, this is 2, and this is 3. So each gas will exert certain pressure, and that is called partial pressure with respect to 1, partial pressure with respect to 2, partial pressure with respect to 3. When you combine all the three gases, you form a mixture. The total pressure exerted by the mixture, according to Dalton's law of what? Partial pressures is equal to what? P total is equal to P1 plus P2 plus P3 plus, P3, correct? So because there are three gases I have taken, right? Okay. So here this 1, 2, 3 are what? They are number of moles. Fine. Okay, fine. Then what we know that according to ideal gas equation, just now we have seen, what is ideal gas equation? Ideal gas equation says that PV is equal to nRT. PV is equal to nRT. Yes. So I can write this equation as P is equal to nRT by V. Yes, I can write it like this also. So if I say from this equation, let me call this equation as 1, let me call this equation as 2, let me call this equation as 3. If I consider under this equation, if I consider P as partial pressures, then with respect to gases 1, 2, 3, can I write it as partial pressure with respect to gas 1 is equal to N1. What is N1? Number of moles. R remains same. It is universal gas constant. And they have said at certain temperature and fixed volume. So V and T and V also will not change. So this is P1. P2 will be what? It will be equal to N2 because number of moles vary. RT upon V again remains same. P3 will be what? It will be N3 RT upon V, correct? So what will be? Can I substitute all the three equations in equation 1? Therefore, I can say P total will be equal to what? It will be equal to P1 N1 RT upon V plus N2 RT upon V plus N3 RT upon V. Is that right? So when you mix all the three gases, what is common here? N1 plus N2 plus N3. I will write one side and common things are RT by V. Yes. What is N1 plus N2 plus N3? N1 plus N2 plus N3 is nothing but what? It is nothing but N, total number of moles. So N is equal to N1 plus N2 plus N3. Is that right? So this is the equation P total for P total. Now what if I want to take the ratio of the partial pressure of gas 1 with P total? Yes, the ratio of partial pressure of gas 1 with P total. So what will I get? P1 upon P total. What is value of P1? N1 RT upon V. What is P? Can I write N1 plus N2 plus N3 as N RT upon V? RT upon V gets cancelled. So P1 upon P total is equal to what? N1 upon N. Correct? What is N1 upon N? It is nothing but mole fraction. It is nothing but mole fraction. Correct? So let us see here. So N1 plus N2 plus N3R is equal to N. According to ideal gas equation, PV is equal to nRT. If this equation 2 is true, then it must be true for each gas in the mixture. So P1, partial pressure with respect to 1 is N1 RT by V. Similarly, P2 is equal to N2 RT by V. P3 is equal to N3 RT by V. And we know that P total is what? P1 plus P2 plus P3, where P1, P2, P3 are partial pressures with respect to gas 1, 2, and 3. So when you substitute N1 RT by V plus N2 RT by V plus N3 RT by V, RT by V is common, therefore we will take it aside. N1 plus N2 plus N3 RT by V. Yes? Okay. So I will write it as P total is equal to N1, N2, N3 plus N2 plus N3 RT by V. If you take the ratio of P1 upon P total, it will be N1 by RT upon V. Yes, upon N1 plus N2 plus N3 RT upon V. RT upon V gets cancelled. What remains? N1 upon, what is this N1 plus N2 plus N3? It is N, number of moles, total number of moles, N. And what is this? It is mole fraction. It is mole fraction, correct? Are you all understanding? So it is mole fraction. Therefore, we can write it as P1. I will mention it here. I can show you what will be the final equation from this. P1 is equal to, what is N1 by N? It is mole fraction with respect to component 1. Take P total this side into P total. So if you want to find the partial pressure and express it in terms of mole fraction, what will be the equation? P1 is equal to mole fraction X1 into P total, total pressure. Is that right? So P1 is equal to X1 into mole fraction. This is how we express partial pressure in terms of mole fraction. Partial pressure in terms of mole fraction. So this is the expressing partial pressure in terms of mole fraction. You can see here Xi, that is I is mole fraction of some gas I. X is what? Xi is what? Mole fraction of some gas I is equal to partial pressure of I upon total pressure. Or you can write partial volume of I upon total volume, or number of moles of I upon N total number of moles, where Xi is the mole fraction of gas I in a mixture of N gases. N denotes the number of moles and P denotes pressure, V denotes volume. You can write it like this, or else only in terms of pressure if you want. Pi is equal to what? It is equal to Xi into P total. This is the correct expression for partial pressure and mole fraction relationship. So partial pressure with respect to gas I is equal to the product of mole fraction of gas I and the total pressure exerted by the mixture of gases. Total pressure exerted by the mixture of gases. So this is about the Dalton's law of partial pressure. Dalton's law of partial pressure. So here you can see the mole fraction of a specific gas in a mixture of gases. It is equal to the ratio of partial pressure of that gas to the total pressure exerted by the gaseous mixture. Yes, this mole fraction can also be used to calculate total number of moles of the constituent gas when total number of moles in the mixture is known. Furthermore, volume occupied by the gas in a mixture can also be calculated with this mole fraction with the help of the equation provided below. Please do remember this equation. So Xi is equal to Pi upon P total. So it is ratio of partial pressure of a gas to total pressure of the gaseous mixture, and that is equal to what? Mole fraction. Different formula for mole fraction. Or using this mole fraction, you can even calculate the volume occupied by a gas to the total volume of the gaseous mixture. Or you can even calculate the mole fraction can be used to calculate the number of moles of I, ratio of number of moles of I to the total number of moles. So using this mole fraction, we can calculate all these terms. I can give you a simple example. Yes, I'll just show you an example to understand this. See, suppose, let me say I have a mixture of hydrogen gas and oxygen gas. Okay, and they both exert total pressure of 1.5 atmosphere on the walls of the container. If the partial pressure of hydrogen is 1 atmosphere, find the mole fraction of oxygen. Find the mole fraction of oxygen. See what all is given. Partial pressure of hydrogen gas is given. How much? 1 atmosphere. Correct. Total pressure is given of the mixture. How much it is given? 1.5 atmosphere. You applied Dalton's law of partial pressure. P total is equal to what? It is equal to partial pressure of hydrogen plus partial pressure of oxygen, because these two, they are the gases. Find partial pressure of oxygen. It will be partial pressure of oxygen will be equal to what? Total pressure minus partial pressure of hydrogen. So 1.5 minus 1 comes out to what? 0.5. So partial pressure of oxygen is what? 0.5. They have not asked us partial pressure of oxygen. They have asked mole fraction of oxygen. Therefore, mole fraction of oxygen, what is the formula? It is the partial pressure of oxygen divided by the total pressure. Correct? Total pressure. What is the partial pressure of oxygen? 0.5. What is the total pressure? 1.5. So 0.5 upon 1.5. 5 ones are 5, 5 3s are 15. So it comes out to 0.33. So mole fraction of oxygen is 0.33. And this is a unitless quantity. It is mole fraction is a unitless quantity. Is that clear? So this is how we find the mole fraction using Dalton's law of partial pressures. Using the Dalton's law of partial pressure. Yes, even you can find partial pressure of gases if the number of moles or mass is given. Yes, those are different ways of expressing the Dalton's law of partial pressures. Now, what are the applications of Dalton's law of partial pressures? The application is that it is helpful in determining the pressure of dry gas. It helps in determining the pressure of dry gas. I'll tell you how. Okay. See, first application is it helps in determining the pressure of dry gas collected. Let me say over water. When a gas is collected over water, when a gas is, say, collected over water, when it is collected over water, just imagine you have a container of water and gas is collected over water, it becomes moist. Correct? It becomes moist. Due to what? It becomes moist due to water vapor. Water vapor. Yes, which exerts its own partial pressure. Its own partial pressures, correct? So because of its own partial pressure of water vapors, the gas becomes moist. Yes, this partial pressure of water vapor, this partial pressure of water vapor is called aqueous tension. It is called what? Aqueous tension. Yes, understood. So when a gas is collected over water, it becomes moist. Why it becomes moist? Because water vapor exerts its own partial pressure. And this partial pressure of water vapor is called aqueous tension. It is called aqueous tension. So you can write the partial pressure of the dry gas is equal to what? It is equal to partial pressure of moist gas, or you can say it is equal to partial pressure of total gas minus the partial pressure of water vapor. Water vapor, correct? When you minus it, you will get the partial pressure of dry gas. Yes, or I can say the partial pressure of dry gas is equal to moist gas, or you say total pressure minus what is partial pressure of water vapor? The partial pressure of water vapor is called aqueous tension. It is called aqueous tension. Yes. So this is one application of aqueous. This is one application to determine the partial pressure of the dry gas. You can use this formula. Total pressure minus aqueous tension. What is aqueous tension? Partial pressure of the water vapor. When you subtract it out, you will get the partial pressure. Even you can calculate the relative humidity. Application of Dalton's law, you can calculate the relative humidity. It is denoted by the symbol RH. Relative humidity is nothing but it is the ratio of, it is what? It is the ratio of partial pressure of water in air, partial pressure of water in air to vapor pressure of water. To vapor pressure of water. So you can calculate relative humidity present in the atmosphere. Yes, at a given temperature, it is equal to RH is equal to partial pressure of water in air to the vapor pressure. This is not aqueous tension. Pressure exerted by vapor pressure is aqueous tension. So vapor pressure of water. Yes, that is how you find the relative humidity. Even you can calculate what? This is second application. Even you can calculate what? You can calculate the mole fraction. And we know mole fraction of some gas, say I, is equal to what? The partial pressure of gas I to the total pressure of the mixture. This is how we calculate the mole fraction. So these are the three applications. Finding the partial pressure of dry gas, finding the relative humidity, and also calculating the mole fraction of a gas in a mixture, gaseous mixture. But there are certain limitations of this Dalton's law. The limitations are, yes, this law is applicable only when the component gases in the mixture do not react with each other. So it is applicable only when, it is applicable only for non-reactive gases. It is applicable only for non-reactive gases. The gases should not react with each other. For example, N2 and O2 you can use, CO and CO2 you can use, N2 and Cl2 you can use, CO and N2 you can use. Understanding? You can use these. These are non-reactive gases. You can use these two pairs of gases. Pairs of gases you can use. But this law is not applicable to gases which combine chemically. It is not applicable. It is not applicable to gases which combine chemically. It is not applicable to these gases. Yes, like for example, you cannot say I will take two gases H2 and Cl2. You cannot take H2 and Cl2 and separate partial pressure with H2 is partial pressure of H2, partial pressure of Cl2. You cannot mix them and say P total is equal to P1 plus P2 because they will combine chemically and form HCl. Correct? Similarly, you cannot take CO and Cl2. It will form COCl2 gas. You cannot take NH3 and HBr and NH3, HBr, and you cannot take HCl. You cannot mix these three gases and say I will calculate total pressure is equal to P of HCl plus P of NH3 plus P of HBr. No, all these will react together chemically. Nor you can take NO and O2. NO and O2. So these pairs you cannot take because they will combine chemically. They are reactive gases. So what is the limitation? Dalton's law of partial pressure is applicable only for non-reactive gases such as only such pairs. N2O2 non-reactive, COCO2 non-reactive, N2Cl2 non-reactive, CON2 non-reactive. But if you take reactive gases, they will combine chemically and the total pressure will not be equal to the sum of partial pressures. Yes, another law which is really equivalent to this law, yes, of partial pressure and related to partial volumes is known as law of partial volumes. It was given by Avogadro, a scientist. What this law says is when two or more gases which do not react chemically, they are kept in a closed vessel. It says, same like Dalton's law of partial pressure, the total volume exerted by the gas is equal to mixture, gaseous mixture is equal to sum of partial volumes of the individual gases. And so on up to Vn. So this is law of partial volumes. It was given by Avogadro. and law of partial pressures was given by Dalton. Yes, similar to that of partial pressures. Yeah, so this is about Dalton's law of partial pressures, and these are the applications. And just now we have seen pressure of non-reacting gases are generally collected over water and therefore are moist. We have seen just now. Pressure of dry gas can be calculated by subtracting vapor pressure of water from total pressure of moist gas. And what is the vapor pressure of water called? It is called aqueous tension. It is called aqueous tension. So pressure of, it is not 2, it is dry gas only. Pressure of dry gas is equal to P total minus aqueous tension. P total minus aqueous tension. Correct? Moving to the next one. Kinetic molecular theory of gases. Kinetic stands for what? It stands for something which is in motion, right? Okay, so you can see here molecules of gases are taken in a closed vessel. They are continuously moving and we know the properties. They may collide with each other and change in the direction, or they may collide with the walls of the container and exert pressure. Therefore, this kinetic theory of gases, it relates what? It relates macroscopic property of gases like temperature, volume, pressure. It relates these macroscopic properties to microscopic properties, say speed, momentum, and position. Yes. In this model, what we are going to see is the atoms and molecules are continuously moving in random motion, constantly colliding with one another. You can see there, and with the walls of the container within which the gas is enclosed. Okay, it is this motion that results in the physical properties. So when this motion occurs, when they hit the walls of the container, when this motion occurs, there is what? It results in the physical properties such as heat and pressure. So let us go deeper into this, let us delve deeper into this kinetic theory of gases and try to understand. What is kinetic theory of gases? See, we know that the gases are made up of large number of molecules. Yes, consider H2 gas. It is made up of large number of H2 molecules. O2, large number of molecules are there, and they are moving in a random direction. They are moving in they are moving very fast in a random direction, and they have certain speed. Okay, by knowing their speed or the position, one can figure out the macroscopic particles properties. That is, macroscopic means what? By knowing the speed or you say position, you can say what is the temperature, or you can say what is the internal energy of that gas molecule. Yes, you should be able to figure out. Understanding. So based on this, some assumptions were made. So kinetic theory of gases makes some basic assumptions. So let us try to understand what are those basic assumptions, and then we will move to the postulates. The basic assumptions of kinetic molecular, so only the name says molecular theory of gases. The basic assumptions made are molecules do not interact with each other. Interact with each other. Second is collisions between the molecules. You can say collisions between the molecules or to the walls will be elastic. That means energy is neither released nor absorbed when these collisions are occurring. Third, momentum is conserved. Kinetic energy is conserved. So these were the basic assumptions. These were assumptions. Okay. So how this kinetic theory of gases was derived? Yes, how it was derived. So with this, what conclusion they came to was there were certain concepts in kinetic theory of gases. The significance of this theory was by knowing the temperature, we can directly figure out the kinetic energy, because we know that temperature is directly proportional to kinetic energy of the gaseous molecules, no matter what gas you are considering, until and unless it is an ideal gas. Knowing the macroscopic parameters like pressure and volume, you can accurately calculate momentum, velocity, and internal energy. This was what kinetic theory said. Yes, this was what kinetic theory of gases said. So what does this theory speaks about? What are the postulates of this theory? Let us try to understand. Kinetic molecular theory of gases. It says this theory was being developed. Kinetic molecular theory was being developed by many scientists. Bernoulli used this, developed Bernoulli, Joule, Clausius, Maxwell, and Boltzmann all together developed this kinetic theory of gases. They represented dynamic particle, or you can say macroscopic model for the gases. Okay. What are the postulates? What are the postulates of this kinetic theory of gases? The theory says gases consist of large number of very small identical particles called atoms or molecules. Every gas you consider, it consists of large number of small particles and they are called molecules. Further, the theory says they are called molecules and they are moving with very high velocities in all possible directions. In all possible directions. They are moving with very high velocities in all possible directions. So gases consist of large number of very small identical particles called molecules. In terms of noble gases, we call them atoms, right? And they are moving with very high velocities in all possible directions. The actual volume occupied by a gas molecule is negligible in comparison to the empty space between them. So what does the second point says is the volume occupied by individual gas molecules. See, when we consider gaseous state, there are many gas molecules. The volume occupied by the individual gas molecule, it is negligible. It is almost zero compared to the total volume of the gas. When you compare the total volume of the gas, the volume occupied by individual gas molecule, it is negligible. It is almost zero. Yes, this is the second most important point. So first point says what? Please do remember these points because with these points, they came up to next conclusions. First point says gases, any gas, it is made up of large number of minute particles, identical particles, and they are called molecules. And they are moving with very high velocities in all possible directions. Correct. Next very important point is the volume occupied by individual gas molecule is what? Is negligible. It is negligible compared to total volume of the gas. When you compare to the total volume of gas, the theory says the volume of individual gas molecule is negligible. Next point what it says. Third point what it says is gases can occupy all the space available to them. This means they do not have any force of attraction between their particles. So what does the third point says? The gaseous molecules, they occupy all possible volume. Therefore, there is no force of attraction between molecules of gases. So there is no force of attraction between the molecules of gases. This is the third point. Particles of gas are always in constant random motion. So they are moving in all possible directions. When the particles of gas are in random motion, pressure is exerted by the gas due to the collisions of the particles with the walls of the container. So when gaseous molecules hit the walls of the container, they exert the pressure. Collisions of the gas molecules are perfectly elastic. Gas molecules, they have perfectly elastic collisions. Means what? This means there is no loss of energy after collision. That means when the two molecules hit each other, when the two molecules collide each other, so collisions of molecules are perfectly are perfectly elastic. That means when they collide with each other, there is no loss of energy. There is no loss of energy after collision. There may be only exchange of energy between the colliding molecules. There might be exchange of energy. So there is no net loss of energy during the collisions, it says. At a particular temperature, distribution of speed between gaseous particles remains constant. Distribution of speed between gaseous particles remains constant. That means at constant temperature, I can say average kinetic energy of all the gases is same. Average kinetic energy of all the gases is same because the average kinetic energy of the gaseous molecules is directly proportional to what? It is directly proportional to temperature. Yes, it is directly proportional to temperature. So average kinetic energy is directly proportional to temperature. Further, what it says, pressure is exerted by the gas when it collides with the walls of the container. Therefore, pressure is due to what? Pressure of a gas is due to continuous bombardment of the gas molecules on the walls of the container. Further, it also says that the effect of gravity on motion of the molecules is negligible. The effect of gravity is also negligible. One more what important point it says is, it says that gaseous molecules, they are considered as point masses. They are considered as point masses because it says, the kinetic theory says, because they do not possess potential energy. They do not possess potential energy. There is no potential energy to the gaseous molecules. So the attractive forces and the repulsive forces between the gas molecules are negligible. So only it says there is no force of attraction between the molecules. They are considered as point masses. There is no potential energy. Therefore, attractive and repulsive forces are negligible. In gas molecules. So these are the postulates of kinetic theory of gases. These are the postulates of the kinetic theory of gases. And on basis of these postulates, what they did was, the scientists, they gave the equation on the basis of above postulates. Following equation was being derived. The equation was PV is equal to 1 by 3 m into n into URMS square. Yes, where P stands for pressure exerted by the gas, V stands for volume, M stands for average mass of the molecule, N stands for number of molecules, and U or VRMS stands for root mean square velocity. RMS, root mean square velocity of the gas. Even they calculated the kinetic energy of one molecule. So kinetic energy of one molecule is equal to half into mv square. If you take n molecules, it is half into mnv square, where v will be RMS, root mean square velocity. Yes, so if n is equal to 1 mole, if I say n is equal to 1 mole, then how do you write? Kinetic energy of 1 mole of gas will be equal to half into m into n into v square, and that will be equal to 3 by 2 PV. 3 by 2 PV. You will get it to this value, 3 by 2 PV, because PV is equal to what? PV is equal to 1 by 3 mn v square. Yes, and solution of this will come out to 12.47 joules. Yes, so all these are nothing but they are the explanations of kinetic theory of gases. So this equation, or what this kinetic theory of gases says, that kinetic energy of a gas depends only on the temperature. It depends only on the absolute temperature, and it is also known as Maxwell's generalization. Kinetic energy depends only on temperature. It is known as what? It is known as Maxwell's generalization. It is known as Maxwell's generalization. Yes, kinetic theory of the gases is directly proportional to temperature. So if you take temperature is equal to 0 Kelvin, what is 0 Kelvin? It is absolute zero or absolute temperature. Yes, and it is equal to what? It is equal to minus 273 degrees Celsius. At this temperature, kinetic energy will also be equal to what? 0. Thus, I can say absolute zero is the temperature at which molecular motion ceases. Absolute zero is temperature at which molecular motion, motion of the molecules, molecular motion stops, or you can say ceases. It stops. Yes, because kinetic energy is directly proportional to temperature. It is directly proportional to the temperature. So this is all about kinetic molecular theory of gases. Kinetic molecular theory of gases. But this was not being accepted. Yes, this was not being accepted because there were certain changes. There were certain changes. So that was nothing but a deviation from ideal gas behavior. So what do we mean by real gas and ideal gas? See, what is an ideal gas? Gas which obeys gas law or ideal gas equations, PV is equal to nRT, at all temperatures and pressures is called ideal gas. Yes, or it is also called perfect gas. Yes, almost all the gases, if you see what present gases are there, they will not obey ideal gas equation at all temperatures and pressures. Understanding? And those gases are called real gases. So gases, you can say, if you see the difference between ideal gas and real gas, I can say that the gases tend to show ideal behavior more and more as temperature increases above the boiling point. Thus, I can say a real gas is that which obeys gas laws under very low pressure. You can define real gas like this, which does not follow ideal gas behavior under all conditions of temperature and pressure. Or I can say real gas is that which obeys gas laws or ideal gas equation under very high temperature and very low pressure. Under very high temperature and under very low pressure, the real gases behave like ideal gases. So only at these two conditions, the real gases behave like ideal gases. Otherwise, at any other conditions of temperature and pressure, if you see, the real gases will not behave as ideal gases. They will not behave as ideal gases. Understanding? Okay, therefore, what is an ideal gas? The gas which obeys gas laws or ideal gas equation, which is ideal gas equation, PV is equal to nRT at all temperatures and pressures is called an ideal gas, or you call it as real gas. If you look at almost all of the gases, I will show you the graphs also. Almost all the gases, they deviate from ideal behavior. That is, no gas is perfect, no gas is ideal. And the concept of perfect gas is only what? It is only hypothetical. Hypothetical means what? It is only ideal. It is theoretical. Yes. Then what are our real gases? The gases which do not obey ideal gas behavior, that is ideal gas equations, or you can say which do not obey ideal gas laws at all conditions of temperature and pressure are called real gases. Because these real gases, they tend to show ideal gas behavior as the temperature rises, that too when? Above the boiling point, and when the pressure is lowered. When temperature is increased above the boiling point and when the pressure is lowered, they will show ideal behavior. And such gases are called real gases, or you can call them as non-ideal gases. So what are real gases? Real gas or non-ideal gas is that which obeys gas laws or ideal gas equation under very high temperature and very low pressure. And this deviation, you can explain it by plotting pressure versus volume, as you can see here the graph, or you can also explain this behavior for different gases by plotting pressure, product of pressure volume versus pressure. Yes, that we will discuss in the next class. For now, I hope you have followed what is ideal gas equation, how we can derive it, what is Dalton's law of partial pressures, what are the applications of Dalton's law of partial pressures, and even what is a real gas and ideal gas, and deviation from ideal behavior. So real gas will obey ideal gas equation only at very high temperature and very low pressure. So till now, whatever we have discussed the concepts, please do practice them. In the next class, we'll go with further concepts of the topic. Thank you.